Hi, I'm Jordan Ward-Graber, and today I'm going to be talking about Besting the Quizmaster, Crowdsourcing Incremental Classification Games. This is joint work with Brianna Satnoff and Hal Daume. We're all at the University of Maryland. Just to give you a bit of a roadmap, I'm first going to talk about incremental processing and how it contrasts with what's typically done in machine learning settings. I'll then talk about how one particular trivia game is an example of humans doing incremental processing of data. We'll then talk about techniques for getting a bunch of examples of humans going through this process, develop machine learning algorithms that can also process data incrementally, and then I'm going to end with a brief advertisement about why you might want to consider using these data. So first, what typically happens in a machine learning problem is that you're trying to learn a function that maps x to y, and this function f looks at all of x. And if you think about it, this isn't what a human would do. A human, if you asked someone to look at a pile of books and sort them into stacks based on what the books were about, they wouldn't meticulously read every word in every book. They would flip through the pages, get a gist of what's going on, and then put the book in the appropriate pile without exploring any more of the book. This isn't what machine learning algorithms do. They look at every feature in a single example. I'm going to call such algorithms rapacious because they consume all of the example. And people have looked at algorithms that aren't rapacious. And one way of addressing such problems is to process data incrementally. That is, features in X are revealed one by one, and the algorithm gives an answer when it's ready. And this has been studied a lot when the costs of each feature are known, particularly in decision trees. And in contrast, we're going to investigate a task here that's inherently incremental. And that task is called Quiz Bowl. So Quiz Bowl is a game typically played between schools where you have two teams in a room and a moderator. A moderator reads a question, and when a team knows the answer, they hit a little button called a buzzer, and they buzz in. They then give an answer. If it's right, they get points. If it's wrong, they lose some points. And there are hundreds of these teams all around the U.S. taking part in this activity almost every weekend. But this is easier to understand through an example. So I'm going to read a question and think about when you would be able to answer the question. A letter from Bernard Chomsky first made the argument that all DPs must have it. Chomsky called IPs faulty because its assignment in sentences with verbs like believe can change the specifier in a process called its exceptional marking. In Russian, the ending for the instrumental one is and in German, des is an article for the genitive one. For 10 points, name this linguistic feature that signifies whether a noun is a subject when it's nominative or an object when it's accusative. And the answer here is case. One thing to notice is that the clues in this question are structured pyramidally. That is, they go from very difficult, obscure things to things that are more obvious by the end of the question. And this is what allows Quiz Bowl to serve as a good differentiator of what team knows more about any particular subject. If you know more, you'll be able to answer the question earlier. At this point, I like to mention how this is different from Jeopardy! So Jeopardy! Is a trivia game. It has buzzers, but those buzzers are only operational at the end of the question, and thus it doesn't do as good a job of discriminating who knows more about a particular topic. Quiz Bowl, on the other hand, does. And there are thousands of questions written every year, large question databases, teams practice on these questions, sometimes online. Is there any way that we can take advantage of this process and get a better understanding of how humans process data in these incremental contexts? And so in order to do that, we built a crowdsourcing platform so that people could play Quizable online. And here the questions were revealed word by word. We thought we were going to have to pay people to play these questions, but it turned out to be so fun that we got lots of questions, tens of thousands in the space of 2 weeks, just because people had so much fun playing these games. And the data we got was really interesting. So if you look on the left, these are all of the words that appeared in questions where the answer was Wuthering Heights, a 19th century British novel. And it's this big undifferentiated mess. But if you look on the right, these are all of the places, all of the words that immediately preceded a place where someone buzzed in and answered the question. And you can read off of this word cloud exactly what people know about Wuthering Heights. So it's a novel featuring Heathcliff and Catherine, written by Emily Bronte, that takes place at Thrushcross Grange. And so these questions are doing a good job of exposing people's knowledge, and where they answer the question discriminates what features are salient about this novel in people's minds. And we use that information to improve standard Rapacious machine learning tasks, but I'm not going to talk about that here. If you're interested, please look at the paper. What I'm going to talk about instead is a little bit more fun, and that's what you have to do in order to build a Quizable playing robot. So we're going to treat this as a Markov decision process with a very simple state space. You can either buzz now or you can wait. And in order to build the system, we need 4 things. One is a content model that's going to generate the guesses of our algorithm. So because the action space is very, very simple, and it's an abdicated responsibility of what to answer, we need something else to tell us what to answer, and that's going to be the content model. The content model is constantly generating guesses, and the second thing that we're going to need is a policy. Now the policy will tell us when we should trust the guesses that the content model produces. We're going to learn this policy from an oracle that's going to be trained on examples, and we need features in order to tell us a rule for generalizing from our training data to unseen data. And I'll talk about each of these in turn. So first, the content model. So the content model is a Bayesian generative model with answers as the latent state. This was trained on Wikipedia pages. And the content model is just going to have a constant, it's going to always have a posterior distribution over the possible guesses. And the policy will tell us when we should take a guess from the content model. And our guess is always going to be the argmax of this posterior distribution. The oracle is going to basically tell us on some training data when our content model was guessing correctly. So we take a bunch of questions, reveal portions of these questions, and see in what sorts of conditions the content model can guess correctly. So sometimes it's wrong, and other times it's right. So here are 3 examples of training data that our oracle is providing to us. And we're going to use this as training data in order to learn a policy. So the policy is a mapping from state to action. We're going to use a classifier, which is a standard technique in reinforcement learning when you have examples of good policy behaviors. And it's going to use features such as how much of the question you've seen, what text of the question you've seen, and also what the posterior distribution looks like. This is clearer through an example. So as we start to see part of a question, that induces a posterior distribution over possible answers. And at first, it's a very entropic distribution. We don't know what's going on. So the content model has a guess, but it's not very good. We encode this as features, taking the specific words that have been seen, taking what the content model is guessing, and features that encode the rough shape of the posterior distribution. We then show that to our classifier, and the classifier that's been trained through the oracle tells us wait. And so we wait, we see more of the question. We now represent that as a collection of features. So we have all the features that we had before, and in addition we have features that tell us how much the posterior distribution has changed since we saw these additional clues. And so these features tell us, oh, we have a new guess, a different guess than we had before, and the max of the posterior distribution has gone up a little. So we feed those features again into the classifier. The classifier tells us we should still wait. So we see a little bit more of the question. We represent that as features. And now our posterior distribution is very peaky, and it's fairly confident, and the confidence increased a lot since last time. So in these sorts of situations, we should buzz. And when we buzz, that says, yes, you should answer now. So you look at the posterior distribution, you take the argmax of that distribution, and that's your answer. In this case, Julius Caesar, which is correct. And so now we have everything we need in order to simulate a game with the human data that we have. And so what we do is we show questions to our algorithm and see where it buzzes. If it buzzes before a human, it wins. If it buzzes after, it loses. And we have a payoff matrix like so. It basically says 10 points if you're right, 5 points if you're wrong. Okay, so there's still some outstanding questions. So what human actions do we actually compare against? What I'm going to talk about here is taking the median buzz for every question. So a bunch of people answered the question correctly. For every question, you take the median one of those. So that's a relatively strong baseline. Does the algorithm that I discussed here do better than obvious Rapacious baselines, where you don't do any of this crazy incremental stuff and just basically have cutoffs? And so yes, the details are in the paper. And how do features affect the performance of this algorithm? As it turns out, most of the features do help a little, but only a handful are very, very useful. More details about this in the paper. The good thing is none of these features actively hurt performance, so we just threw them all in. Okay, so how are we doing? So, not so well. If our content model is just a naive Bayes model, we don't do so well. We're losing almost 1.5 points, or more than 1.5 points, for every question that we hear. And so what we can do to fix this problem is make the content model a little bit smarter. And the content model should know what kind of questions there are, what kind of categories could you be asked in a Quiz Bowl game. So humans do the same thing. They figure out the category first, and then they restrict their search space to that category. And this prevents crazy wrong answers that a naive Bayes model often gave. So, for example, it would answer entropy on a question about Johannes Brahms, when a much more reasonable guess would be Robert Schumann, because both Brahms and Schumann were 19th century German composers. And the content model should also know how questions are structured, so that you can understand titles, quotes, relationships. And we're going to do that by having our content model have a notion of categories and also a simple language model. This is a very dumbed down version of Wood and Tay's doubly hierarchical language model from 2009. So short story, our content models are now going to know about the categories, they're going to know about bigrams, and hopefully they'll do better than a naive model. Okay, so if we add in just knowledge about categories, we start to beat the humans. So getting a little bit per question on average. If we just add in the language model, it helps a little, but not very much. But if you add in both categories and language model together, we finally start to pull ahead of the humans. And this is as far as we've gotten. We're still not beating the very best players, so where can we improve? Um, so there is some simple stuff. There are a number of questions that we're getting right, but it's just a little bit too slow. And I suspect that there's some feature engineering there that we could do that. Um, there are also some questions where we're not getting the question type correctly. So the question has clues telling us that the question is about a human, this man, this Italian, and so on a question about Enrico Fermi, and we're answering things like electric field. And if we could tell that the question was looking for a human, we could restrict the answers to those where the human is correct. And then in other cases, we simply don't have enough data. Some of these questions are very obscure, and we simply need to know more in order to get these questions right. Okay, so in the last part of this talk, I'd like to briefly discuss why you might want to consider using Quizbowl data. So you can think about a Quizbowl question as a bunch of summaries that have a very particular structure. And that is that the things that are well known should be at the end of the question, and you shouldn't have a lot of diversity. But things at the beginning of the question should not be well known, and you should have a lot of diversity there. And one of the nice things about thinking about this as a summarization problem is that you have lots and lots of examples of these summaries. For popular answers, you have hundreds of summaries all about the same thing. And here are some examples. So here are a bunch of clues from questions about the Choson Dynasty. One tomb of a king from this region is named for the depiction of an eight-legged heavenly horse found there. So talking about rulers, talking about religion, talking about economics, talking about philosophy. So these are all very diverse clues that appear at the beginning of the question. But if you look at the end of these questions, they're all very similar. And you have very different ways of expressing the same thing. Name the successor of the Goryeo dynasty. Name this dynasty that ruled Korea until annexed by Japan in 1910. Name this dynasty which succeeded the Goryeo, the longest lasting dynasty of Korea. What was this final imperial dynasty of Korea? So you have very diverse ways of expressing basically a paraphrase of the same final clue. Another thing you might want to tackle with Quizbowl questions is references. And the neat thing about Quizbowl questions is that good Quizbowl style says that you should only use references that correspond to the answer. And so here's an example about a question on the Hanseatic League. And so I'll highlight all of the references in this question, and together with the constraint that the clues should be pyramidal, the constraint on references leads to a very interesting effect. So this entity, this group, this polity, this Northern European Trading League, all of the references are about the Hanseatic League, the answer of the question, and as you move through the question, they get more and more specific. And so it's sort of like you're reading off hypernym relations off of WordNet. Okay, so to conclude, I talked about Quizbowl. It's a fun game with lots of data. It's connected to lots of natural language processing and machine learning problems. And we hope to continue working on this problem to improve models so that we can have smarter systems. and also have strategies that adjust to the kind of opponent that you're playing. So we had very simplistic strategies here that had no knowledge of their opponents. I think that there's some really interesting game theory applications for these questions, and we have lots of data of humans playing this game that we hope we can learn from. Thank you very much.